Hello all, welcome to this course on time series modeling and forecasting using R. Now we are almost done with the current week, and then just to summarize as to where we stand this week. So the broad topic we studied this week was co-integration and of course causality towards the end, right? Now again we have a practical session which is the last session of this week, and then as you see we have opened up a fresh new code which is code 8 for the current week, which is week 8. Okay. So just to tie all the things down, we'll work with a few ideas about, let's say, co-integration using different scenarios, and then maybe how can one perform some co-integration tests on, let's say, a set of time series variables and so on and so forth. Okay. So before we proceed with any of the practical stuff, or let's say the coding material, just to remind you very quickly as to what exactly one means by co-integration. So let's say again, if you have not really revised any of the sessions which have happened this week, then a strong suggestion would be just to go back and then just try to revise all the videos for this week, especially the topic of co-integration, causality, pertaining to, let's say, the different tests of co-integration, so on and so forth. Okay. But the broad idea about co-integration is that even if you have two time series variables or time series processes, let's say xt and yt, and let's say even if individually both the time series processes, let's say xt and yt, are I1, and again what do you mean by I1? So I1 means integrated with a certain order of 1, right? So integrated with an order of 1 means that both the series individually are non-stationary, of course, since they are integrated, and integrated with a certain order of 1 means that if you difference each of the series individually once, right, or a single time, then one can actually get a stationary series. Okay. So the integration actually defines the number of times one has to difference the series in order to make it stationary or convert from a non-stationary series to a stationary series. Okay. So this is the broad idea about what do you mean by integrated with a certain order. Now again, going back to the definition of co-integration. So let's say if you have two time series processes xt and yt, which are, let's say, integrated with an order of 1, but if at all we can find a certain co-integration vector, let's say with a coefficient beta, right, such that the linear transformation of xt and yt along with, of course, the coefficient beta happens to be I0, or in other words, even if xt and yt are individually I1, or let's say integrated with some order, let's say in general d, but if there exists some linear combination of xt and yt, so let's say xt plus beta into yt, or something like that, such that this entire linear combination happens to be I0. And again, what do you mean by I0? So I0 means integrated with an order of 0, which means that the underlying linear combination is stationary. Okay. So if at all such a thing happens, then we will say that xt and yt are co-integrated. Okay. So again, just to summarize in one sentence, is that even if xt and yt are individually integrated with some order d, but if there exists some linear combination with that co-integrating factor beta such that the linear combination happens to be stationary or I0, then one can say that xt and yt happen to be co-integrated. Okay. So hopefully, one again strong suggestion is that if you don't know or if you don't recollect any of the definitions we covered this week, then again you have to go back, of course, and then view all the videos again, or maybe take some notes before you actually put forward to do the practical session which we will cover today. Alright. Okay, so again in front of you, you see a window, and then you have couple of libraries which one requires. So the first one is URCA, and then second one is VARS, or variables. And of course these are not new libraries. So we've been studying these libraries even in the last session, of course last practical session, and so on and so forth. Okay. So we'll quickly incorporate these two packages inside the R environment by hitting run. Okay. So the first one is URCA, and then the second one is VARS. Right. And again, just a couple of things that since you have missed any of the factors, any of the points from last practical session, is that obviously you will have to install these two packages first, either by going here into tools and then hitting install packages, or you can simply type in install.packages and then within brackets the name of the package. Okay. So hopefully once you install the packages successfully, it should show you a small message here that the packages have been installed successfully, something like that. And once you install the packages, then you can actually load them in the R environment. Okay. And even after you load them in the R environment, it should actually throw you this message that loading the required package, let's say sandwich, lmtest. So by the way, these two packages are inbuilt in one of these two packages. Okay. So you need not, by the way, install these two packages separately. So if you are installing URCA and VARS, then obviously these two are hidden packages inside these two. Okay. So R just tells you that what inbuilt packages one has in the packages you are basically loading now, something like that. Okay. Okay. So hopefully once you install the packages and then call them in the R environment, then we'll play around with the practical data set upfront, which is the Canada data set. So data and then Canada in brackets. Now again, if you're not very sure as to what this data set means, so probably one can actually type in something like question mark and then Canada. Here it comes, right? And then if you hit enter or simply run, then on the right hand side it will show you a small description of the underlying data set. So this data set, the name is Canada, and then this is a macroeconomic time series data set. So as you can read the heading as well, and then it sort of throws you a small description. So the original time series are published by the OECD, and then the sample range is from the first quarter of 1980 until the fourth quarter of 2000. So this is just a small description about the timeline of the data set. And then the following series have been utilized in the construction of the series provided in the data set named Canada. So the underlying data set contains all these main economic indicators, by the way. So unemployment rate, and then manufacturing real wage or consumer price index, etc. Right? And by the way, each of these variables have their own codes in the data set as well. Right? And then the later part of the data set contains quarterly national accounts. So let's say the Canadian nominal GDP. So by the way, this entire data set is revolved around the GDP or the underlying macroeconomic factors of Canada. Okay. And probably the next thing is labor force statistics. So one can actually go ahead and then read all the variables which are sort of involved. So here you see the short forms of all the variables involved in the data set Canada. For example, production, employment, etc. All right. By the way, yeah, so this is the description. So PROD or prod is a measure of productivity or production. E is used for employment, U is the unemployment rate, and then RW stands for real wage. Okay. So hopefully the data set is clear. So again, one small point I like to make is rather than jumping directly into all the coding and then getting bogged with all the coding, one should actually first get a feel of the data set first. I mean, what variables the data set contains, right? And then what do each and every variable means. So in our case, what would be the focus variable? So all these points one should actually take a note of that. So rather than simply jumping directly into the coding one by one, right? Because this could be really mind boggling. I mean, once you load a data, but then if you don't know that what goes inside the data or what variables the data set contains, then the entire code is of no use basically, right? So once you load any data set in the R environment, let's say Canada or for that matter any other data set, one should actually go variable by variable and then try to understand that what's going on inside each and every variable in the data set. Okay, so hopefully once you load the data set Canada inside the R environment, then we'll give a slightly different name. So Canada underscore TS, which stands for time series. And then this line, which is line 7, just converts the data set in a time series framework. Okay. And here you can mention the starting year, so 1980, and then frequency is 4. So you have a quarterly data set. Okay. So one can run this. And then again, just to tell you or just to show you as to how the plot of some of the variables inside the Canada dataset look like, then we can actually plot them. And here we are actually only plotting the first 4 columns. So you can actually specify which columns the plot should contain. Okay. So I'll run this and then show you the plot. So this is exactly how the plot looks like. Let me zoom in. Okay. All right. So you see a heading which tells you Canada macroeconomic data, and on the left hand side you can see all the variables of interest. So unemployment rate, real wage, productivity, and then employment. And then this is just a visual way of checking that how each and every variable should behave. So for example, employment grows over all those years, right? Same is true for real wage, same is true for productivity. But when you come to unemployment rate, you can see some seasonality there. Can you see that? So let's say unemployment is not that high initially, but probably it picks up in some of the in-between years, let's say around 1983 or 84. But then again, by the time 1990 arrives, the unemployment again comes back to the same levels and again picks up. So you can see some sort of a seasonality or periodicity in the unemployment data set, right. So, a strong suggestion is that even before you try to analyze any data, and then I have repeated this number of times even before. So, the very first thing one should do is try to plot the underlying data and the underlying variables, just to get a feel of how the variables are behaving over time. I mean, are you seeing any trend in the data? Are you seeing any seasonality in the data, right? Are you seeing any noise or let's say changing variance patterns in the data, right? So, all these things could be kind of really clear if you plot the data in the initial stages, right? Okay, so I'll close the plot now and then go back to the code. And now the very first thing we'll do is to basically check if each of the variables in the data are stationary or non-stationary. And then for that I can use an augmented Dickey-Fuller test or ADF test, right? Now again I will not go into detail of ADF test, as we have covered this even before in one of the earlier practical sessions. But this ADF test kind of tells you that whether a series is stationary or not, alright. And here you can actually specify a few things in this ur.df. So ur.df is the name of the test, which is ADF test, and we'll give it a name, something like ADF underscore test underscore E. And then here, like I said, you can actually tweak some of the input values here. For example, one can mention type to be drift, right? And then select lags. So select lags is AIC. So it sort of selects automatically the lags based on the least AIC values and so on and so forth. Alright. Okay, so we'll run this ADF test and then I can get a summary of the ADF test, and then in the console you can get a summary of the ADF test. So initially it tells you the fitted regression line, so it tells you test regression drift, right? And then by the way, so this is the name of the test. So augmented Dickey-Fuller test for the unit root, alright, which of course tells you whether the series is stationary or not. And then this is the linear model is trying to fit. So the first difference fitted on the first lag plus a constant which is 1 plus the first lag of the difference, right? And this is the coefficient of the estimated regression line and so on and so forth. And then down the line it also throws you the R square value of the fitted regression line, which is let's say 0.52, etc. And of course the p value. So p value is really small. So if p value is small, what do? So you'll be rejecting the null, right, and then going with the alternative, right? And down the line it tells you the value of the individual test statistics. So let's say minus 0.29 for the first one and then 2.17 for the second one. And the very last thing it tells you is that the critical values for observing or rather comparing the test statistic values. For example, the first one is minus 0.29 or let's say minus 0.3 roughly for us, and then that minus 0.3 value should be compared to any of the first row that you see here, any of the critical values at 1% point, 5 percentage point or 10 percentage point. And then so clearly one can see that if you take the absolute value of this test statistic, it happens to be 0.3, right, and 0.3 is less than any of the absolute values that you see here, right, which means that one can't reject the null. Okay. Similarly, if you go with the second one, the test statistic value is 2.17, and again the same story. So 2.17, since it's less than any of the critical values, again one can't reject the null basically. Okay. And again, if you remember, if you go back to one of the earlier practical sessions we've covered, the null hypothesis in ADF test is that the series is not stationary, isn't it? So the null hypothesis is that the series is or the underlying series are not stationary. The alternative hypothesis in ADF test is that the underlying series is stationary. So here, since you are not able to reject the null, we can actually say that both the series individually are not stationary. Here. Make sense so far? So this is exactly how one can apply the ADF test on. The only difference here is that we are applying ADF test on multiple series, right? And then since we are applying on more than one series, you can see a small change in the syntax here. Okay, so now the next thing we'll do is we'll cover an array of co-integration tests, and again probably in the last session or the last to last session we've covered the entire theory behind how to develop the co-integration test, and then what exactly do you mean by applying a test for checking for co-integration, and then what all co-integration tests one has, right? So from that theory session, if you remember, one of the very famous tests was Johansson test, right? So we'll try to apply this Johansson test on some of the variables. So the name is Johansson co-integration test, and again quickly just to remind you that what exactly is the null hypothesis. So null hypothesis is no co-integration, of course, and then the alternative hypothesis is there exists some co-integration between the series. Okay, so we'll give it a name again. So let's say JO underscore test, something like that, And now the underlying function to be used is CA.JO. So CA.JO means Johansson test. So JO stands for Johansson test, right? And now we'll be applying this Johansson test on which variable? So on the time series generated variable of the dataset Canada. Okay, so Canada underscore TS. So again remember the original dataset was Canada, and then we converted the dataset in a time series framework, right? So and then that name was Canada underscore TS. So whatever tests you apply, always make sure that you are applying the tests on the time series variant of the dataset. For example, Canada underscore TS, etc. Okay. And again inside this Johansson test, you need not pay much attention, but just to let you know that you can actually tweak a few values even here. So let's say type equal to trace or k equal to 2, right? And then ECDET and then spec, so transitory. So all these are kind of part of the syntax themselves. All right. Okay, so we'll run this Johansson test first, right? And then again we can run the summary of the Johansson test. So summary applied on JO underscore test. Again, if you come down, if you scroll down in the console, so it sort of throws you a lot of things here. And probably I'll try to explain a few ideas from the output here. So the name is Johansson procedure, of course, and the test type is trace statistic without linear trend and constant in co-integration. So here you're kind of ignoring any linear trend and a constant in the co-integration values. Now the next output thing that you see here is all the different eigenvalues that you have. So and of course all these eigenvalues are small if you see. The first one is 0.0539 because this is 5.39 into 10 to the power minus 1, which is roughly 0.0539. Next one is 0.026, right? The next one is 0.012, etc. Right? And as you see, the eigenvalues kind of reduce in the magnitude. So the biggest eigenvalue is this one, which is 0.053. Okay. And now the most important part in the Johansson test is the values of the test statistic and the critical values of the test. So again you see a small table here. On the left hand side you see different values of R. So again remember what R means. So R is the rank of the co-integration matrix. Okay. Again just to repeat, R stands for the rank of the co-integration matrix. In other words, R tells you that how many variables are apt for taking or rather for considering co-integration. Okay. So would they be 0 or would they be 1, would they be 2 or would they be 3, alright. So this is exactly what the first column tells you, and then of course the values of the test statistic in the next column and all the corresponding critical values in the second, third and the fourth column. So at different percentage points, so 10, 5 and 1. Okay. So this is exactly how one should read the Johansson test output. So the first column that you see gives you the rank or the optimal rank of the co-integration matrix. The second column gives you the actual test statistic values, and all the three columns that follow give you the corresponding critical values for that particular test statistic value. Okay. Now again, how do you conclude anything from here? So again you start from bottoms up, let's say. So the first value is that you see is R equal to 0, let's say, and again as you clearly see for R equal to 0, the value of the test statistic is pretty high, which is 105.84, and again clearly this value happens to be bigger than any of the critical values at any percentage points. So if the value of the underlying test statistic happens to be bigger than the critical values, then one can reject the null hypothesis safely, right? And if you are rejecting the null, we can actually reject the claim that R is 0 and then go for the next level. Is this hopefully clear that you go one by one? So at the value of R being 0, we are able to reject the null, so we can move on. Okay. Now the next value is R is bigger than 0 but then less than equal to 1. Okay. And now what happens? So again the underlying value of the test statistic is 42.31, and again clearly 42.31 is bigger than any of the critical values at 10%, 5% or 1%. So again we will reject the null and then we will again ignore this level here and then move on. Okay. Now the next one. So by this time we know that R is not equal to 0, R is not equal to 1 also, and then R has to be bigger than 1. Okay. So the next value or the next level is R is bigger than 1 but then less than equal to 2. Now what happens? So the underlying test statistic value is 17.39, and here you can clearly see that 17.39 is less than any of the critical values. Alright. So if the test statistic value happens to be less than the critical values, we accept the null hypothesis, isn't it? So the exact opposite. So we accept the null hypothesis, and then if we accept the null or fail to reject the null, then we can actually go, or we have to go with this level, which is r is less than equal to 2. Now, once you accept the null hypothesis or fail to reject the null at any level, there is no point of going beyond that. Okay, make sense? So, from this one can actually conclude that r is bigger than 1, but less than equal to 2. Okay, again just to summarize, r is bigger than 1, but less than equal to 2, and why exactly? Because we stopped here at this level. So, from this level we concluded that we can actually accept the null hypothesis or fail to reject the null, and hence we can actually fix this value of r, which is less than equal to 2, right, but r has to be obviously bigger than 1. Make sense so far? Okay, and again the next thing it throws you are the eigenvectors. So, both the eigenvalues as well as the eigenvectors for each and every variable in the series. So, employment, productivity, real wage, and then unemployment. Okay. So, this sort of tells you, or this gives you a matrix, because you have eigenvectors corresponding to each of the time series. Okay. And now the last thing it tells you is the loading matrix. So, loading matrix is nothing but the weights matrix, right. So, again if you remember, for the Johansson test it requires some underlying weight factor on each of the time series variables. So, this is the underlying weight matrix. Okay. Okay, so this is a summary of the Johansson test. So, again I've specifically written down in the small comments here that the underlying Johansson test applied on the Canada data set suggests r has to be bigger than 1, but less than equal to 2, which means that one needs a linear combination of two series for stationarity. So, since the conclusion is that r is bigger than 1 but less than equal to 2, so we can actually take a linear combination of two series to achieve stationarity basically. So, this is the ultimate conclusion of the Johansson test. So, one has to identify the appropriate value of r, let us say either 0 or bigger than 1 but less than 2 or bigger than 2 but less than 3, right. And once you identify the particular value of r, then the value of the underlying r means that one requires the linear combination of how many time series to achieve stationarity. Okay. Make sense? So, here again just to summarize one last time is that in this case one requires a linear combination of two different series to achieve stationarity. Now, the next thing is just if you want to convert the Johansson test result to a VECM representation or the error correction method representation, then one can do that, and probably we are not going to detail here. So, let me just quickly run this and then summary of the underlying VECM model. But now the more important part is forecasting with ECM. So, again I have written down forecasting with ECM or a error correction model, and then for this method you by the way require to convert the Johansson test result to a VECM. So, I will say that this small chunk is a requirement for forecasting. Okay. So, the first thing for forecasting is that we will try to fit a VAR representation if needed for forecasting. So, VAR stands for vector autoregressive, and then we will give it a name, let us say VAR underscore model, and then this is the underlying function or the inbuilt function. So, VEC2 VAR applied on the Johansson test, r is 1. Okay. So, we will run this first and then forecast. So, once you fit the model or once you fit the VAR model, then forecast for 10 time steps ahead, because n dot ahead is 10. Okay. So, again r has an inbuilt command called as predict. We have been using predict number of times even in a few last practical sessions as well. So, forecast and then predict of the fitted VAR model, and then how many time steps ahead? So, 10. Okay. So, we will run this, and then now the last thing to do is plot the forecasts, right. Now, again one point to mention here is that generally what happens is if your plot is very large, right, then R can throw this error. It says that error in plot.new figure margins are too large. So, in that case what you do is you basically run this code, okay, you basically run this code and then again run the plot command one more time. Okay. So, now can you see the plot? So, let me zoom in. Okay. So, this is the forecasted plots, and then it sort of tells you that after you apply the VAR model, then this is exactly how the individual series would forecast. So, forecast for the employment rate, then productivity, real wage, and then unemployment. Make sense? So, this is exactly how the forecasting exercise looks like. And now the next thing we will do is we will play around with a few other co-integration tests apart from Johansson test. Okay. So, again we will incorporate on the same data set which is Canada. So, we will again call the same data set. And here if you remember from the Johansson test, it kind of concluded that one requires the linear combination of two series. Okay. So, here we will only focus on two series. So, the first one is productivity and then second one is employment rate. So, Y is productivity and X is employment. Okay. Now, the first test we will cover is the Engel-Granger test and then we will give it a name EG_test. Alright. So, this tells you the Engel-Granger test and then summary of the test. So, again, so just to remind you one thing, that the summary of the test, the only thing one should watch out for is the value of the test statistic and the underlying critical value. So, again here one can see that the test statistic value is 14.33, which is less than any of the critical values. So, one fails to reject the null. And if you fail to reject the null, then we can say that residuals are non-stationary or series are not co-integrated. And hopefully the same conclusion would be we can get from the Johansson test as well, right. So, now the only difference between this Johansson test is that this is only applied on the two variables. So, X and Y, which were productivity and employment. So, summary of the Johansson test. So, again the same conclusion, that residuals are not stationary and then series are not co-integrated. Okay. And now the last thing we can do is we can run the Granger causality. So, does X causes Y or does Y causes X, right. So, can we somehow speak anything about causality between X and Y. Okay. So, again on the same data set. So, data set is Canada and then here we can difference the data set once to achieve stationarity, because again if you remember, Granger causality can only be applied if the series is stationary. Okay. Now, choosing the lag length. So, we can choose a particular lag length again based on the minimum AIC value. Then we can fit a VAR model, right, on the different series, and the last thing is we can perform the Granger causality test. Okay. And here we are performing if E Granger causes the other variable, which is, so here we are testing if the employment Granger causes the productivity. Okay. And for this we have this Hoppe's test, right. For checking this we have this Hoppe's test, alright, and then again we will input Y and then X and then fit some ARIMA models, extract the residuals, right, and then calculate the cross correlations between the residuals, then calculate the Hoppe's test statistic, right, and then compare that with the chi-square critical values, and then this is the result. So, Q statistic and then the p value. So, p value happens to be 0.32, which is bigger than the null hypothesis. So, we fail to reject the null, and if you fail to reject the null, it says that no causality exists between the series. Okay. So, I sort of rushed through the later part of the code, but again take your time, right. So, since you already have the code, so spend some more time on exploring more about, let us say, the causality aspect. So, we spent a whole lot of time on co-integration, but not that much on causality. So, again a strong suggestion is that go back and try running the causality aspect of the code one more time. So, try to understand that whether employment Granger causes productivity, or how do you apply this Hoppe's test, so on and so forth. Okay. Thank you.